Hi, this is Andy Wade. I'm a meteorology student at the University of Oklahoma. I've spent summer 2013 at the National Weather Service Forecast Office in Birmingham, Alabama, researching QLCS and supercell tornado environments. My mentor for this project has been Kevin Laws, the Science and Operations Officer at Birmingham, and this project contributes to NOAA's goal of creating a weather-ready nation. Before we begin, there are a couple definitions we need to know. We've been using a fairly loose definition of QLCS, just a linear complex of thunderstorms, or a squall line, that may have some smaller nonlinear features. Those would be the features we're interested in when talking about tornado environments. And of course, a supercell is just a single thunderstorm with a long-lived, strong rotating updraft. These are radar examples of each of these cases. Of course, when issuing tornado warnings, the goal is to catch as many tornadoes as possible without issuing many false alarms. Since the beginning of the storm-based warning era, that's exactly what the National Weather Service in Birmingham has been doing with discrete supercell tornadoes. 94% probability of detection, 67% false alarm ratio. As you might imagine, the problems begin when we introduce QLCS scenarios. Half of these tornadoes are going unwarned. Meanwhile, 3/4 of warnings being issued in these scenarios turn out to be false alarms. Work on this problem has been ongoing at the Weather Service in Birmingham. There's a pre-existing database containing every tornado and every tornado warning within their county warning area dating back to October 2007, the beginning of the storm-based warning era. To every entry in that database, we added a storm classification by convective mode, for example, QLCS, Classic Supercell, or HP Supercell, among some other more specialized classifications. We found that of the 253 tornadoes the county warning area has experienced in this time, 27% have been QLCS tornadoes, 50% have been discrete supercell tornadoes. When comparing QLCS and supercell tornado cases, we've left out the hybrid or mixed mode cases that may exhibit characteristics of both QLCSs and supercells. This is one example of that. You can see two well-defined supercell structures within a larger line that also qualifies as a QLCS. There's a common perception that QLCS tornadoes tend to be weak and brief. We actually found that to be true across all storm modes within our database. Most tornadoes fell into the EF0 or EF1 classification on the enhanced Fujita scale. It's true that most of the most intense tornadoes are produced by discrete supercells. But while QLCS tornadoes rarely reach the higher end of the EF scale, they do pose a significant threat to life and property. Because of this, it's essential to expand our understanding of supercell and especially QLCS tornadoes. This may translate to more accurate forecasts and warnings. Ultimately, that would move NOAA and the National Weather Service toward the goal of a weather-ready nation. If we can increase probabilities of detection, that may save lives. Minimizing false alarms reduces disruption from severe weather events. We classified 126 overall severe weather events by the dominant storm mode, using the tornado database and the storm mode classifications contained in it. Environmental data taken from Storm Prediction Center mesoanalysis was already contained in the database for most of these events, and we combined this information with our convective mode classification. We looked at the environments for 47 supercell events and 50 QLCS events. We'll begin with the supercell findings. This is surface-based CAPE with supercell events by tornado production. We've defined a third category on the far right, high producers. Those are events that produce 5 or more tornadoes. You can see there is little or no correlation between supercell tornado production and surface-based CAPE in this plot. This was typical of most of the environmental parameters we examined in both supercell and QLCS tornado events. We did find one individual parameter that appeared to be a good predictor of supercell tornado production. That was 0 to 1 kilometer storm relative helicity. This agrees with existing literature on supercell tornado environments. In general, combinations of parameters were more effective. For results we found to be statistically significant, we've given the p-values for the difference between producers and non-producers. In our box plots, our whiskers represent the 10th and 90th percentiles of the dataset. This is 0 to 1 kilometer storm relative helicity, and again, it's the best single environmental predictor of tornado production in supercell events. We also looked at some traditional combined parameters used widely in severe weather forecasting. This is the supercell composite parameter. As you can see, there is a considerable amount of overlap between producers and non-producers. The significant tornado parameter produced somewhat more useful results in supercell events. The Energy Helicity Index, or EHI, 0 to 1 kilometer layer, turned out to be a fairly effective predictor of tornado production in supercell events. We also tried some of our own combinations through experimentation, and this turned out to be our highest performing parameter or combination of parameters for supercell events. It was able to correctly identify 85% of supercell events in our database as producers or non-producers. Moving on to the real problem, which is QLCS tornadoes. We found no single environmental parameter, not even storm relative helicity, that's able to effectively predict QLCS tornado potential. Once again, combinations of parameters proved to be most effective. If you'll remember, in supercell events, 0 to 1 kilometer storm relative helicity was an excellent indicator of tornado potential. There is no such relationship among our QLCS events. The medians for producers, non-producers, and even high-end producers in 0 to 1 kilometer helicity are almost identical. 0 to 6 kilometer shear vectors oriented perpendicular to a QLCS are widely considered to be favorable for severe weather. We didn't find the amount of 0 to 6 kilometer shear normal to the QLCS to have any bearing on tornado production. There seems to be a stronger relationship between instability and tornado production in QLCS events than in supercell events within our database. Higher Cape QLCS events tend to produce more tornadoes. This may be because more of our QLCS events are very low Cape compared to supercell events. Interestingly, supercell composite parameter produces statistically significant results comparing QLCS tornado producers and non-producers, even though this isn't what the parameter was designed to do. However, you can see there's a considerable amount of overlap between producers and non-producers on the box and whisker plot, and this may be a case where statistical significance does not translate to operational usefulness. We see similar results here with the significant tornado parameter. Energy Helicity Index produces somewhat better separation between producers and non-producers, but quartiles still overlap to some degree. We start to see a larger difference when we combine more parameters. This is the first combination we tried that produced results this helpful. This is a simpler combination that produces interesting results. The difference between most unstable and surface-based Cape over surface-based Cape was used as an indicator for low-level instability, low values of this indicating unstable low levels. We found that nearly all of our QLCS tornadoes occurred when this ratio was below 1/2, while most of our non-producing events fell above 1/2. Combining these results with some parameters related to the mid and low-level wind fields, we were able to achieve 82% accuracy in identifying QLCS events in the database as tornadic or non-tornadic. This was our highest performing combination of parameters in QLCS events. Overall, we did find some differences in QLCS and supercell tornado environments, especially in 0 to 1 kilometer storm relative helicity, as was shown in the box plots. This may suggest different mechanisms of tornado formation within QLCSs as opposed to supercells. Existing research would support this conclusion, as it proposes multiple different mechanisms of tornadogenesis within QLCSs. From here, we would want to test our best performing combinations of parameters on a much larger data set. We would want to do this before thinking about any kind of operational use of these parameters. Another possible avenue for future work could be high CAPE or warm season versus low CAPE or cold type events. More cases are needed to draw any conclusive results from these. There's also a problem of defining warm and cold season in the southeast. We found that there are many higher CAPE events in the winter and quite a few cooler type events in the spring. So again, we found 0 to 1 kilometer storm relative helicity to be our most useful parameter in supercell events. We found no such correlation among individual parameters for QLCS cases, but combinations of parameters were our most effective for both storm modes. A little bit more about these combined parameters we've presented. They are dimensionless, similar to EHI, SIGTOR, and supercell composite. They're not intended to represent physical quantities in the atmosphere. These are not magic numbers. In studying these cases, we've learned that there is no silver bullet in severe weather forecasting, and none of these parameters can replace the judgment of an experienced forecaster. These are simply intended to be tools used to assess tornado risk in the Birmingham County warning area based on the environments that have produced and not produced tornadoes in past events. This knowledge may be used to formulate a warning strategy accordingly, and possibly improve probabilities of detection and false alarm ratios.